the sections on polarization, scattering of light, and rainbows. And then we'll move ahead today to, this is a handout that you can pick up if you haven't gotten it already. We'll get started with electric forces, which is a fundamental transition in what we're going to be doing this semester. Reminder that our quiz is a week from today, and that will not include anything on electrostatics. That everything that I cover today could be a possibility for the exam. And where I wanted to start is with polarization. Recall that before we had defined an angle of refraction in such a way that if we have unpolarized light coming in, some of the light will refract and still be unpolarized. But because light is a transverse wave, we make an angle of 90 degrees to the direction of the refracted and reflected rays, we get something that's just plain polarized, like this. And so that means that the wave energy is going this way, but not this way. Okay, so this in and out, just a reminder, that's this motion. It's just a representation for that motion. So you've got something that looks like this. The up and down is represented by this, and the in and out, like this, it's coming out at you, is represented by that. So this is the in and out, that dot. Okay, and so the in and out, as it comes up, satisfies angle of incidence equals the angle of reflection. But when that angle is what we call the Brewster angle, then the reflected rays are plane polarized. And so if you're sitting here near a swimming pool, then is it correct that you want to have the polarizers in your sunglasses oriented like this? No. No. Why is that not correct?
It's going to let that light through.
It lets that light through and would screen out the light that gives you useful information about the world, which is all the rest of it. And so that doesn't mean you won't get useful information about the world from this component too, but it'll be preferentially weighted in favor of bright light, which just burns your retina out and doesn't help you resolve anything. It just gives you bright splotches when you look at it. So this is not what you want. And so as the wave energy comes in, comes down like this and then up, this kind of motion, if the polarizer here, these are like little picket fences, what we've got here in this polarized plastic is these little polymer crystals that are plane polarized to only let light through in one direction. And so if it comes down and it comes back up like that, then I see all of that reflective glare. If I turn it this way, then I screen out the reflective glare and I just let through the vertical component. And so that's the whole key to this. And we saw last time that theta Brewster was the inverse tan of N2 over N1. And so what we got for that then was, I think it was 53 degrees? From the vertical. If the interface is water and air, so this is water and air, then that's the inverse tangent of N2 over N1. That's 53 degrees from and that's your plane polarized reflected waves. There are other applications for this, but let me just show you for a second what happens if you have a horizontal polarizer like that. Here's another horizontal polarizer. And so I can see you just fine through both of them because it's letting through this part of the light, but it's not letting through this part of the light. But now watch what happens if I rotate one of them by 90 degrees. Then you don't see a thing. Okay, and so that's taking out the other component of the light. So a lot of times what you'll have then it's not quite this simple, but in the 3D glasses at a theater, you could do it this way, although it doesn't work out quite as well. You could have one of your 3D glasses polarized vertically, one polarized horizontally. Then the vertical orientation of the polarized light could be slightly offset in angle from the one that's coming in from this direction. And so then basically what you're doing with your two eyes is you're seeing something with a little bit of parallax, the way that you would if you were looking with your two eyes at a real physical object. And so this then allows for the illusion of 3D images and that sort of thing. And so your brain then just takes that information and it turns it into a picture, just the same way as it would if you had light coming in from slightly different directions and you use that to give you depth perception. That's what these polarizers do. Although I don't really like those 3D glasses because they kind of strain my eyes after a couple of days. I don't think they have it quite right, so your eyes have to strain a little bit, at least mine do, to see it properly. And but you know, with better perfected techniques, they should be able to work that out. Now it turns out that they don't do it quite this way. This is the simple version. But there's also what's called circular polarization. And so instead of having orthogonal coordinate system that's based on x and y, you can have it based on something that's polarized in a right-handed sense and something that's polarized in a left-handed sense. And you can get your orthogonal basis vectors from that. And so in other words, instead of x and y, you can have your independent components be left and right circular polarization. The advantage of doing that is that if you turn your head with it like this, then that throws everything off. But it doesn't. You can turn your head left and right circular polarization, and it doesn't affect it's not dependent on what your x and your y axis are. And so circular polarization is slightly more mathematical than I have time to get into here. But it turns out that it's actually easier to make polarizers that are left and right circularly polarized than it is to make ones that are polarized plain like this. And one of the reasons for that is that regular crystals, when you send light through them, will naturally tend to make the light come out either left or right circularly polarized. So that's an application of that. You can also use polarization, say, in liquid crystals. And so here's an example of a liquid crystal. Turn this on real fast here. That's on. So I can press on it, I can generate a little bit of pressure, and I can create a polarization. And that polarization then allows for different components of light to travel through the liquid crystal. And so you can do this with an electric field too. An electric field can cause your polarizers to change their angle. And by doing that, you can control the relative distributions of red, green, and blue light that are coming out to pixels. Okay? And so liquid crystal displays then are one of the, although there are other ways of doing it now that I think are even more efficient, that's one of the ways of using polarization to help electrical devices work. Okay, and so that's the main things that I wanted to talk about with respect to polarization. Are there any questions about that? Okay, next, let's look at the scattering of light. This is a selected topic. Polarization, I'm pulling that back out from chapter 33. So that's something that you can still see on the quiz, that it's from the first chapter in the light section. I believe rainbows is also in that. So I'm coming back to a couple of these topics as applications now that we've gone through the whole thing. And one of the reasons why have been waiting to do rainbows is that rainbows actually depend not only on polarization, but also on diffraction to a certain extent. The other thing that I want to look at, which isn't in the book, is scattering. So what's scattering? Well, scattering is just the bouncing of light off of molecules we're talking about atmospheric scattering, then it would be molecules of air. But there are other types of scattering. So for the atmosphere then, these scatterers are molecules either of nitrogen or oxygen in the diatomic state. And so it turns out that the amount that light bounces rather than is passed through a molecule depends on the size of the wavelength relative to the size of the molecule. And so scattering then has a strong dependence, very strong dependence, on size of molecule versus wavelength of light. You may recall that we had the Rayleigh criteria for being able to resolve one image as being separate from another. That had to do with the first interference maximum of one peak of a single slit diffraction being no closer than the first interference minimum of the other peak. But Lloyd Rayleigh got into a lot of other stuff too, and so this is a relationship that he derived. And so our scattering then, according to Rayleigh, is proportional to the frequency to the fourth power. And so that means that how big of a frequency of light you have is related to the scattering by this very high power of the frequencies. Okay, now higher frequency means shorter wavelength. F equals C over lambda. So higher frequency means shorter wavelength. Okay. And so essentially what this is telling us then is that blue light has a much shorter wavelength than red light. For blue light, lambda blue is about 400 nanometers. But for red light, it's about 700 nanometers. Get my colored pens out for this. So what that is telling us then from this relationship is the higher frequency blue light has a shorter wavelength and therefore is scattered much more than the red light is. So this is almost a factor of 2 to 1 in the wavelength. Not quite. Remember, that was kind of the answer to that question as to why the first and the second order patterns didn't overlap and the second and the third did. Had to do with the fact that the ratio of the wavelengths was less than 2 to 1. But let's just say, just for a simple, easy calculation here, that the ratio were 2 to 1. Then how much more blue light would you scatter? Assuming equal intensities of red light. How much more would it be if it goes like the frequency to the fourth power? If we assume, this is just a very crude assumption, that F blue is equal to approximately 2 times F red. It's actually 7/4 bigger, not 8/4. But if we assume that it's 2, then it makes this calculation pretty easy. Then how much more scattering do you get? 16 times more scattering of blue light than red light. Okay, so if this were true then F blue would be equal to 2 times F red. This is to the fourth power. And so that's going to be 16. 2 to the fourth power is 16 times F blue for the scatter. Okay. Or if you just took the ratio of the two, this would be 2 to the fourth divided by 1 to the fourth. So that'd be 16. So if you just took the scattering of blue divided by the scattering of red, and they're proportional with the same proportionality constant, you get 16 times more. But because it's 7/4, we have to do 7/4 to the fourth power, and that's about 11. So this is the actual number of how much more blue light is scattered than red light in the atmosphere. So I can remember when I was very young, jumping on my trampoline, and I asked my grandma, hey, why is the sky blue? And she said, oh, that's easy. The ocean is blue, and so the light from the ocean reflects off the sky. And so you see the sky is blue. And so that seemed reasonable. But then later I realized it was the exact opposite of that. The sky is naturally blue because of the scattering relationship. You have way more blue light bouncing around than you have red light. So the blue light comes in, here are your different molecules, here. And so the blue light is bouncing all over the place, and then eventually it comes in from every oddball direction toward your eye like this, whereas the red light does scatter a little bit, but not so much. So it just kind of comes straight through it. Okay, and so you go, okay, well, if you're so smart, then why are sunsets red? Well, it's the same thing, really. It just seems like maybe a contradiction. But in the evening, near sunset, remember that the light is also bending as it goes through the Earth's atmosphere from the sun. So the sun is actually already set. But what you're seeing, basically, is light that has all the blue light taken out over a much longer path. Okay, so all of this light then from the sun that's blue is bouncing around here, making the sky blue, but you're taking that light away. So what you're left with then is a kind of a reddish color to the sunset. So you see the light that's left. You see the red sunset. Now it's not exactly red. You say, well, it's more orange. But remember, this isn't just either or. It's a little bit of both. And so you have a certain contribution of red, orange, yellow, green, blue, violet, but with ever increasing amounts of scattering. So when you add up all the light that's been subtracted away, what you end up with is kind of an orangish red sunset. And you'll also tend to see this enhanced effect if you go down to Los Angeles and you look at the beautiful, brilliant sunsets down there. And then somebody tells you, well, that's because of smog. Then it doesn't sound so great anymore. But you can have lots of scatters, increased number of scatters when you have more particulate matter in the atmosphere. So you also get that with volcanic eruptions. You know, ones that are really huge that send volcanic dust around, and you can also get that with fires, which we've seen a lot of, which make the smoky skies then look quite a bit more red. Another application of this is with the moon during a total eclipse. During a total eclipse of the moon, you go, well, what good is that if the moon is just in the Earth's shadow? So here's the Earth, here's the sun, then here's the light coming in. It's a combination of all colors. We know that just by looking at the light from a prism. We can see that all of the colors of the rainbow are found in the white light that comes from the sun. Isaac Newton was the first to be credited with discovering this. He did it with a prism. And then he took the light that was refracted from the prism and sent each of the different component frequencies through another prism just to see whether he could break it down farther. But he couldn't. So red stayed red even when he sent it through a second prism, and blue stayed blue. So he concluded from that that those were the elementary components of the light that's coming from the sun. Okay? And so you have the red and the blue coming in and everything else in between. But here in the Earth's atmosphere, you've got all this scattering of the blue light. All the blue light is scattered like that, but there's also a little bit of a bending effect that we talked about before. When light travels through the Earth's atmosphere, it curves a little bit because there's more density near the surface. And so that curve allows for that red light to get to the moon. So the moon is in the Earth's shadow here. This is the total eclipse. When the Earth is between the moon and the sun, this is a lunar eclipse. It's the moon, Earth, sun, and so the moon then is moving this way, moves through the shadow. It's a full moon down here, then becomes an eclipse moon in there, then about 4 hours later it becomes a full moon back out on that side again. And I think last Friday there was a partial eclipse of the moon. It just took a little bite out. And that curvature of the shadow, the Greeks deduced from that curvature that the Earth was a sphere. So the Greeks knew how to analyze this data, knew what was going on 2,500 years ago. But here, the moon will kind of glow this kind of an iridescent orangish color. You don't want to look at it with a telescope because it's not bright enough to get good resolution. But binoculars are the perfect optical instrument to view a lunar eclipse. And so those are all examples then of how the scattering of light can affect what we see. Now if you get all of the light scattered, what you end up with is white light. And so if you have really thick clouds, the clouds will tend to be white, because then all of the light waves are going to scatter, and because they're scattering in every possible direction and they're coming into you from every possible direction, that's a lot of times what you see with an overcast sky with white clouds. Any questions about that? Okay, next, wanted to look at rainbows. And so we've got, from the last handout, we've got some stuff on that. Oh, find that here.